Hello, welcome to the Notes on Graphs for our stats unit. So one of the objectives for the SAT, Objective 4, says given a scatter plot, use linear, quadratic, or exponential models to describe how the variables are related. You will be given a scatter plot and select the equation of a line or curve of best fit. Interpret the line in context of the situation. So check, check. Use the line or curve of best fit to make a prediction. That's the third thing. In Objective 5, you're going to use the relationship between two variables to investigate key features. So you will make connections between the graphical representation of a relationship, properties of the graph by selecting the graph that represents the properties described, or using the graph to identify a value or set of values. The sixth objective is to compare linear growth with exponential growth. So the student will infer the connection between two variables given a context in order to determine what type of model fits best. So those are the three objectives that you're going to have on the SAT that deal with graphs. So the question is, what is a scatter plot? A scatter plot is a graph that displays two numeric values. Let me underline that, or two numeric variables. We use scatter plots to investigate relationships between two variables. There are three aspects of a relationship we could care about. Direction. Is it positive or negative? That's what you want to be able to identify. Positive or negative, and that would be based on slope. The shape. Is it linear or nonlinear? If it's nonlinear, it's going to be a curved relationship. And then the strength of the relationship. Is it weak? Is it moderate, so not super strong? Or is it completely, really very strong? Is a strong strength. So let's look at some examples here of what a scatter plot would look like. This one here has a positive linear association because I could draw a line through it and the points are all kind of pretty close together. It's positive because it's going up, right? A slope that goes up, if you were walking up it would go in that direction. It's linear because it is like a line, and then it would be pretty strong, I would say. This next one over here is a negative linear association because the points are going down. As x, which is this axis, increases, y, which is this axis, decreases. All right, the one below here is a non-linear relationship or association because you couldn't draw a line through these points. It's a curved relationship. Now, those of you who remember from Algebra 1, this would be a quadratic looking because it's a U-shaped, and it would be a pretty strong quadratic. And the last one has no association because these points are just scattered all over the place. They don't have anything to do with each other. It's not like as one variable goes up, the other one goes up, or as one goes down, the other one goes up. Like there's no relationship. It's just totally random points. So let's get into some examples that we have here. The first one says, which scatter plot below shows a strong linear relationship? So, and what type of relationship is it, positive or negative? Remember that graphs are part of Step 3 of the statistic process. After you collect data, a graph is constructed to display the data. So this one would be the linear because it's closer, the relationship between the dots, the points, is closer to a line. Okay, and it would be negative because as x goes up, y goes down. It's a negative, moderate relationship. It's not super strong. There's a lot of points that are kind of off, like over here, but it's a negative, moderate, and linear relationship. That's how we would describe it. This one over here has dots, again, that are kind of all over the place. There's no real, you can't really make a prediction that as x goes up, what would happen to y, because it's just completely scattered. Fitting is the process of constructing a curve or mathematical function that has the best fit to a series of data points. So over here, if you look, this is a curve, and if you remember from last year, this is an exponential decay. So this is showing the value of Judy's car. As the car ages, as it goes up in age, the value of the car is decreasing. Now it's not linear because a car, when you even drive it right off the lot, it loses a big percentage of its value. You're not going to be able to sell it for as much as you bought it for, but then it kind of tapers off. You know, as the car gets older and older, the value is about the same. Often a line of best fit is used to model the data and this line is used to make predictions about the data. A line of best fit is drawn through the center of a group of data points plotted on a scatter plot. We want to have about the same amount above as there is below, and then also ideally your line is going to hit as many points as possible. And that would be the line of best fit, not something like this, or I should have drawn that in a different color. Like if I draw this as a line of best fit, that's terrible. Right, example 2 here. It says the scatter plot to the right relates number of years of education to income level. So the amount of education somebody gets, how many years they spend in school, and how much money they would make. So how would you describe the trend for the relationship to the right? And now, before we even do that, I want to look at this circled point, and just so you understand how to read this, you would draw a vertical line down here to that point and then across over here. So what this would mean is a person who's gotten like 14 and a half years of education is making approximately, I don't know, $17,000. Now, I don't think that's a year unless the education means like 2 years post high school, but I think this means 17,000 maybe even per month if this is education post high school. So this is probably your doctors, your engineers, maybe your people with PhDs, you know, they've gone to school for a long time, they're making a lot more money. So that's how you interpret this graph and that point specifically. So how would you describe this? I would describe this as a linear. It's a linear relationship that is, or I would write, there is a moderate, because you want to talk about strength, positive, because as x goes up, y goes up, and I would say linear relationship between education and income. You always want to include context too. Now, some people may look at this graph and think that it's exponential, like they're like, why isn't it this, like a curve? Well, I could see both arguments, but the thing is, these points, if I was just to remove those points, picture that they're not there, it would not be at all a curve. It would completely be linear. So those few points are influencing it a lot. So you sometimes have to force yourself to ignore those. Those are called outliers, right? Away from all the other data. And those are kind of unusual points that we, don't really consider. Okay, draw the line of best fit. Already did it. Circle the observation that is furthest from the line of best fit. I would say it's this one, right? This is so far from where my line is that's the line that's the furthest. And then part D, suppose the equation for the line of best fit is y equals negative 9,500 plus 1,750x. Explain what the variables or the values negative 9,500 and 1,750 mean. All right, so I'm going to rewrite this equation over here. We should all be familiar with y equals mx plus b from algebra and from first semester of this class. I know that this number that's attached to the variable, that's the slope. We're used to it being this way, mx plus b. This equation is written in reverse order. That's okay. And then this is the y-intercept. All right, so let's look at negative 9,500 first. This is the y-intercept. The y-intercept for any graph occurs when x is equal to 0. So that's going to help us interpret this. So what this is saying is when the number of years of education, that's my x variable, when the number of years of education is equal to 0, a person makes negative $9,500. In real life, like that's always the y-intercept is always what happens when x is 0. And because this is a real life situation, negative $9,500 doesn't make sense. That would mean they owe money. The y-intercept doesn't always make sense in context, but that doesn't mean we don't have to describe it. We still have to. Okay, so now let's look at 1750. Let me change my colors here. Let's do maybe green. Okay, 1750. This is the slope. The slope is known as change in y, whatever our y variable is, over the change in x. So in our problem, y is income. So it's the change in income over the change in years of education. All right, so ours is 1750. So this is 1750 over 1. So this is $1,750 over 1 year. So how would I interpret this? I would say when the years or for every year increase in education, we predict a person or a person's income will increase by $1,750. All right, one thing I just realized writing this one, I should have said when the number of years of education equals 0, a person is predicted to make. We have to use predicted because this line is not for sure, it's what we would predict. A line of best fit is used to predict values, not ones that we know without a doubt for sure. So sorry about that. All right, moving on to the next example. The following scatter plot displays a sample that investigated the number of hours that a participant exercised each week and his or her resting heart rate. So I think everybody knows as you start exercising more and more, your resting heart rate, you build your heart, which is a muscle, I think, and it doesn't have to beat as often to be efficient. You make it more efficient by exercising. You've strengthened it. So the following scatter plot displays a sample of the number of hours that a participant exercised each week and his or her resting heart rate. So for example 3, which of the following represents the relationship between H, the number of hours of exercise per week, and R, the resting heart rate? Okay, if hours per week is my X value, in this case H, that's what has to get multiplied by the slope. So H has to have a number in front of it. So right away, I could cross out option C and I could cross out option D because those don't have H attached to it. The next thing I notice is this is a negative slope. It has a downward trend. So therefore, my answer has to be B. As the number of hours goes up, that's why the heart rate would go down. R equals 79 minus 5H. So 79 would be our predicted heart rate resting heart rate if somebody doesn't exercise at all during the week. That would be the y-intercept, the prediction. And then -5, if I was to interpret that slope, that's saying for every hour extra that you exercise a week, your resting heart rate will decrease by 5. All right, example 4. Use your line of best fit selected above, using it, predict the resting heart rate for a person who exercises an average of 9 hours per week. Grid your answer in on the left. So they are always going to give you at least one of the variables, either R or H. So our equation is the following, the one we found in part 1. And now we're going to plug in, they gave us 9 hours, that's going to go in for H. So 79 minus 5 times 9. So that's going to be 79 minus 45 is going to equal 34. So a person who exercises 9 hours per week, their predicted heart rate would be 34 beats per minute. That's pretty low. So if I was to write this in, I could do 34 like this. I could do 34 like this. Or I could even do, but I don't think I really see people doing it this way, is 34 like that. They either start it or end it. I think just because we write left to right, that's how we would do it. So it'd be 30 and 4. Number 5 here, based on the graph, approximately how many hours does a person with a resting heart rate of 67 beats per minute exercise per week? So this is based on the graph. So we're gonna go to 67 heartbeats per week. That's gonna be about here. And I draw a horizontal line over. Oh my gosh, I actually hit a point. That's very surprising. And then go down to get our answer. It's gonna be approximately 3 hours per week. And the last question here, it says, consider the person in the scatter plot who slept, whoop, no one's sleeping here, they're exercising. It's the opposite, exercised after almost 9 hours. Approximately how many beats per minute higher is the person's resting heart rate compared to what the line of best fit would have predicted? So the 9 hours, we already have it up here. We predicted using our line that it's going to be 34 beats. is the prediction. Now, let's go and see what their actual heart rate was. So almost 9 hours is this person right here. And I would say that their actual resting heart rate going over across here is like 46 to 47. Let's go maybe 47. So approximately how many beats per minute higher? This is the actual heart rate. This is the predicted. Whoops, my writing is terrible. Over here was the predicted. How off are they? They are off by 13 beats. Remember, the line of best fit just gives us an idea. It gives us an approximation. It doesn't give us, the actual value. So they are going to be off. So this person's resting heart rate was higher than what the line would have predicted. This person's resting heart rate is actually lower than what our line would predict. All right, so the second part of this is, again, using the same objective. And now we're going to talk about exponential versus linear and how you're going to be able to tell from a table. We just did based on a graph, looking at it, how you could tell. And now we're going to do it from a table. So here we have a linear growth. It's a line. It's going straight up. It's a growth because it has a slope that is positive. So I should have written maybe positive slope instead of slope positive. Blech. Okay, the decay is a negative slope. On the bottom here, we have exponential growths and exponential decays. You did learn about these, I think, in algebra, unless last year was a little bit different. These equations are actually wrong. This should be y equals a to the bx, and this one should be y equals a to the bx. This is if b, the base, is greater than 1, and this one is if the base is less than 1, but it actually also has to be greater than 0. Okay, so here are where you're going to have to determine how you could tell if it's linear or exponential. So how can you tell if a relationship is linear or exponential based on if they give you a graph or if they give you a table? For a graph, you can tell if it's linear if the shape is, wait for it, a line. Okay, if the scatter plot looks like you could fit a line of best fit, it's a line. And then it's going to be exponential if it is a curve. That either goes, curves up or it curves down. So like this or like this. That is an exponential. The first one's a growth, the second one's a decay. For a table, here's how you're going to be able to tell. For a linear, the slope between any 2 points or any 2 pairs of points will be the same. So what you're going to have to do every time is to calculate the slope twice. This is your job, is to calculate the slope twice between 2 different sets of points. And to tell if it's exponential, basically you're going to be multiplying by the same number each time. So multiply x by the same number each time to get y. If that happens, then it's exponential. Okay, so let's look at our first example here using this table. We have time in hours and amount of substance remaining on some sort of figure. So the first thing I see is that as x is going higher, this is always x, this is always y, as x increases, what's happening to y? It's decreasing. So what we're going to do, we could tell then that it's a decay, because as x goes up, y goes down. Now to tell if it's linear or if it is exponential. I always check if it's linear. I take any 2 points, so I'm going to take 0, 60, and then I'll take the second point, 2, 30, and I'm going to calculate the slope here. The slope is change in y. Remember, slope is y2 minus y1 over x2 minus x1. Tried to write that out of the way, but I wrote it in the way. But anyways, it's 60 minus 30 over 0 minus 2. This is 30 divided by -2, it's -15. This doesn't tell me anything yet. I have to now take 2 other points and calculate their slope. So I could use the same one of my points. So I'll use 0, 60, because 0 is always a nice number to plug in. And then I don't use 230 again, because 2, 30 is going to give me the same slope. I'm going to use 4, 15. All right, the slope of this is going to equal 60 minus 15 over 0 minus 4. I get negative 45, just kidding, positive 45 divided by negative 4. This does not equal negative 15. So therefore, it's not linear. This is going to be exponential. We're going to cross this out because that's wrong. Okay, example 2. What kind of relationship does the following data exhibit? First of all, is it a growth or a decay? Well, as x is getting bigger and bigger, 0, 4, 8, 12, what's happening to the city population? It's going down. So this is definitely a decay. So I'm going to take 2 of the points. I always like to start with the 0 one if it exists, and then I'll take the second point, 4 comma 20,000, and I'm going to calculate this slope. The slope is y2 minus y1, doesn't matter which y you start with, over 0 minus 4. I'm going to get 5,000 divided by negative 4 is negative 1250. Okay, now I take 2 other points. I'm going to use 0, 2500 again, because I like 0. And then let's use the third point, or we could use 12 comma 10,000, whichever one we want. It's totally up to you. I'll use 8 comma 15,000. The slope is going to be 25,000 minus 20,000, or sorry, 15,000. Over 0 minus 8. This gives me 10,000 divided by 8, negative 8, which is equal to negative 1250. So because these are equal, the slope between 2 different points was the same, it is linear. Go ahead and try example 3 on your own. I would like, when you submit these notes, once you're done, that one should be done or else I'm going to take some points off. Okay? Thank you so much for watching. Have a great day. See you in class. Bye.